Hello, my name is Heidi Vreeland, and I'm an ORISE postdoc hosted by USCPA. To preface this presentation, this work is part of the Wildfire Aspire study. These research projects involve local stakeholders in the research process, so our community partners helped us identify their greatest needs and what EPA could do to help. We know smoke negatively impacts health, and this affects communities across the country. The discussions with our partners in Missoula, Montana, and in the Hoopa Valley Tribe in Northern California led us to investigate the effectiveness of clean air spaces during smoke-impacted times. These sites have a history of being regularly impacted by seasonal smoke, and since it's commonly recommended to take shelter from smoke in clean indoor air spaces, we decided to investigate how effective public and commercial buildings really are at cleaning the air during smoky times. We selected buildings in Missoula and Hoopa where we anticipated people would spend a lot of time, including schools and community centers, and we set up air sensor networks at both study locations to measure particulate matter levels inside and outside of these buildings. There are nearly 60 air sensors in total across both sites. And since both of these studies currently are still running through the end of this year's fire season, this presentation will highlight some of our preliminary findings. But first, to give an example of what we see in our sensor networks, here is a screenshot of the sensor network in Hoopa from the PurpleAir Map website. I also included a picture of what a PurpleAir sensor looks like in case you haven't seen one before. Each circle on this map shows where a sensor is located, and darker colors indicate higher PM concentrations or worse air quality. Any sensors you click on will be shown on the plot on the left of the map. In this screenshot, which was taken about a month ago on September 23rd during the Red Salmon Complex fire, I only clicked on outdoor sensors in Hoopa, so this plot shows outdoor PM concentrations from different sites across the valley, and all outdoor sensors show extremely similar trends. Those who have worked with PurpleAir sensors in research before know that when co-located, PurpleAir sensors trend really well with each other, but they still need to be corrected to a higher grade PM monitor or a reference instrument to calibrate the sensors and improve their accuracy. So to calibrate PurpleAir sensors, all sensors were co-located at the start of the study, and each sensor was individually corrected to a near reference instrument, an AirSys EBM in Hoopa and a T640 in Missoula. And the corrections were really similar to what others have seen, including in times of smoke. Since we want to see how outdoor concentrations impact indoor concentrations, we don't want our analysis to include any indoor-generated sources, because that doesn't tell us about how outdoor smoke impacts indoor air quality. Fortunately, we typically did not observe indoor-generated sources across indoor sites. Some exceptions being the senior centers in both Hoopa and Missoula showed indoor sources from breakfast cooking. An example of Hoopa's breakfast cooking spike is shown in the plot here. And a church in Missoula occasionally generated indoor PM from candles and incense used during church services. So to quantify the infiltration of outdoor PM that comes indoors, peaks like this were removed before calculating indoor PM 2.5% reductions. From measurements taken last year in Missoula, we've already seen that reductions vary widely across buildings. This plot shows PM 2.5% reductions from last summer's monitoring campaign of Missoula buildings. In addition to using sensors to measure PM 2.5 levels, we also collected general information from building owners about their facility, including asking about the MERV filter rating used at each building. Higher MERV numbers indicate better filtration, where MERV ratings of 11 or better are suggested for filtering out smoke. We found that nearly all buildings used MERV 8 filters, shown in dark gray in the plot, and only a couple of buildings used filters with higher ratings, shown in blue. Indoor reductions varied widely, even at the same site. For example, here are two indoor spots at the YMCA. This showed that filter rating alone was not a good indicator of indoor air quality. Some additional causes for the observed variation in indoor percent reductions include how many people were opening doors to come in and out of the building, ventilation from open windows or propped doors, the position of the sensor indoors. For example, a sensor placed in a lobby may pick up more outdoor air from door openings compared to a sensor placed in a more interior room. And there are many factors regarding the building's air handling system and maintenance that may have an impact. To improve our understanding of what factors influence indoor reduction across buildings, for this year's study, we brought in an HVAC expert to assess buildings. We found that many building owners didn't know much about their building operations, so the HVAC expert was able to streamline findings across sites in a more comparable way. This also allowed us to collect much more detailed information, including air handling schedules, any gaps and seals that may impact infiltration, and the condition the filters and air handling systems were in. The pictures here show an example of what MERV 8 filters can look like at 2 different sites. All of this information will help us get a clearer picture of what are common issues seen across buildings and which factors seem to have the most influence on indoor reductions. The current status on these building evaluations is that nearly all sites have been assessed in Missoula, but in Hoopa, building evaluations have been delayed due to COVID travel restrictions. The community is currently closed to non-members, so we'll pick up on evaluations in Hoopa once they decide it is safe to move forward. So let's look into an example from Missoula on how this additional HVAC info has provided more context at monitoring sites. Here is an example at the YMCA, which had 2 indoor sensors, one in the YMCA's preschool and the other in the YMCA's weight room. The bar chart on the right shows that in both this year's study and last year's study, we saw higher reductions in the preschool compared to the weight room. The time series plot on the left shows a week of data from mid-September when a smoke plume was impacting Missoula and led to sustained elevated outdoor concentrations. What I want you to notice is that the PM in the weight room, shown in the pink line, shows a similar pattern to the outdoor PM levels shown in the green line, but the preschool does not follow the outdoor trend as closely. If you plot the PM concentrations in the preschool alongside the temperature, you can see that the trend in outdoor temperature matches the trend in PM 2.5 levels in the preschool. When it got hot, the thermostat would kick on, leading to cleaner air being brought into the room. So the set points on the thermostat were indirectly controlling PM levels in the preschool. But why does the preschool trend with temperature while the weight room trends more with outdoor PM levels? And why does the weight room show lower reductions? These pictures show the 2 rooftop air handling units that serve the YMCA weight room and preschool. In particular, these photos show the outdoor air dampers, which can rotate to opened and closed positions, sort of like Venetian window blinds. The outdoor air dampers let outdoor air inside when the dampers are open, which, for example, you may want to do overnight to save energy with cooling the building, or to reduce indoor CO2 levels. But at the YMCA, both outdoor air dampers had failed and were stuck in the closed position. But the weight room had warped panels, and it was described as poorly sealed in the HVAC experts' building report, while the preschool unit showed really tightly closed panels. The red arrow highlights the gaps and poor seal in the weight room unit, which allows outdoor air to more easily infiltrate into the weight room, as compared to the preschool, where the seal was more tightly closed. This is something we would have never known about without the HVAC inspections, so it'll be really interesting to look at all of this in more detail once we have all our data at the end of the study. We are also hoping to learn a lot from these HVAC evaluations for the buildings in Hoopa, where smoke impacts lasted for a longer duration and PM concentrations were much higher. This plot shows hourly PM data in September, but since making these slides, things got a lot worse in early October, when stagnant air led to smoke sitting in the valley at concentrations exceeding 1,000 micrograms per meter cubed. Although building evaluations in Hoopa are currently delayed, I wanted to share an example of reductions seen at the medical center in Hoopa, which is known for having a great HVAC system. We don't know any additional details about the HVAC operations or what kind of types of filters they were using, but to get a glimpse of how well the medical center was able to reduce PM during smoky times, here is one last analysis on the medical center for wildfire data through mid-September, which was all of the fire season data available at the time this presentation was made. The 2 lines in this plot show the time series of daily averaged PM 2.5 indoors and outdoors over the course of the fire data. The X's show the medical center's PM 2.5 indoor reductions, and the green highlighted X's indicate times when the daily outdoor PM 2.5 was above 5 micrograms per meter cubed, which was the case more than 75% of the time. So you can see when PM was above 5, the percent reduction stayed above 65%. In September, when concentrations got really high, with daily PM approaching 250 micrograms per meter cubed, the medical center maintained high percent reductions, which is great to see, but still translates to higher than usual indoor levels compared to typical daily operations. In conclusion, sensors showed similar outdoor PM trends, but indoor concentrations were more variable across sites. HVAC systems can maintain high reductions during smoky times, but sites could benefit from having portable air cleaners on hand for days when there's extremely bad air quality. And we've noticed that a number of sites have HVAC systems that do not operate as intended or aren't fully functional. We saw that air quality was impacted by a number of structural factors, including gaps around the units and doors, and operational settings, including indirect impacts from thermostat set points. Indoor reductions have been observed to vary with time, building operations, and outdoor concentrations, and the new HVAC evaluations added to this year's study have helped to elucidate some of the variations in reductions seen across buildings. Knowing more about HVAC issues could also help building owners make targeted decisions on actionable steps to improve indoor air quality. Sensor networks are useful tools for communities. They can help identify things like clean air spaces during smoky times. But I do want to mention that keeping up sensor networks like these require a lot of work. They require a dedicated on-site staff to deploy and service sensors, and a full-time analyst for data analysis and regular monitoring of sensor health and operations. So thank you for your attention. I will leave you with this slide here showing everyone we would like to thank in Missoula, the Hoopa Valley Tribe, and at US EPA for their help with this work. And you can learn more about the Wildfire Aspire project at the link below. Thanks so much.